experiment, we investigate the motion of a cart on an inclined plane to better understand the concepts of acceleration. This setup is based on Galileo's early experiments where he observed that an object rolling down a slope accelerates due to gravity, and the steepness of the incline directly affects the rate of acceleration. Importantly, he also noted that the acceleration is largely independent from the object's mass. The primary objective of this lab is to measure the acceleration of a cart moving along an inclined air track and compare the experimental values with theoretical predictions. By adjusting the tilt of the track and altering the cart's mass, we will explore how these changes influence acceleration. We will also apply trigonometry, specifically the sine function derived from the Pythagorean theorem, to calculate the incline angle and determine the theoretical acceleration using an equation. Through careful data collection and analysis, we aim to validate key principles of kinematics and understand the relationship between incline, angle, mass, and acceleration. This experiment provides a practical demonstration of how acceleration is influenced by gravitational components along a slope, reinforcing fundamental physics concepts.
Hello, my name is Conrad, and I'll be doing the materials. First off, we have the little slabs, the metallic or the wooden, which is this. And it's the first time we'll be using these. It's to increase the height of the air track. Second, we have the air track and the two stoppers on both sides. We use this to create a frictionless surface. We have the glider, which is actually not over here. The glider is over here. The glider is over here, and this is what moves across the air track. And then we have the air blower, which is at the very back over there, to generate air to push the glider. We have the cable, which will be used to find the Pythagorean theorem. We have the computer with the capstone software. We have the motion sensor as well, which we've used before to measure the motion. We have the mass set, which is the grams. So we have the mass set, which we have two of these, which are 50 or 100 grams, and we use them to change the mass of the glider. We have the ruler. We have the ruler, which allows us to measure the distance of 1 meter and others, and then we also have the balance to measure the weights. That'll be it. Hello, my name is Conrad Su.
And my name is Gregorio Olivas.
And we'll be doing the procedure. In this lab, number 5, we set up the incline by placing the air track on a flat table, and we inserted one or more slabs, wooden or metallic, under the single foot end of the air track to create a small incline. We measured the height of the slabs, the opposite side, and the length of the track, the hypotenuse. We used the Pythagorean theorem to calculate the sine of the incline angle, where the sine theta equals the opposite over the hypotenuse, and we calculated the theoretical acceleration of the cart on the incline, where the theoretical acceleration equals gravity times sine theta, where gravity equals 9.8 meters per second squared. The next part is we collected the motion data. We connected the motion sensor to the capstone software with the computer and made sure the sensor was measuring the air track with several test runs. We opened a position versus time graph and placed the glider halfway up the track within the sensor's range. We started the data collection by releasing the cart gently and let it move freely down the incline, and we stopped the data collection once the glider reached the end of the track. In the data analysis, in the same experiment file, we added the velocity versus time graph, and we used the slope of the velocity versus time graph to determine the experimental acceleration of the glider and compared it with the theoretical acceleration. We calculated the percent error using the formula, where percent error equals the absolute value of experimental acceleration minus the theoretical acceleration divided by the theoretical times 100.
And then in the next step, we change the mass, adding extra weights to the glider evenly on both sides so then the mass is balanced. We recorded the new total mass of the glider. We repeated the previous steps to collect its position, velocity, and acceleration data. We then compared the accelerations with and without extra mass. We recorded the predictions and results and discussed whether mass affected acceleration or percent error. Next, we changed the tilt by removing some slabs or adding more to change the incline of the air track. We measured the new height and we calculated the theoretical acceleration using theoretical equals gravity times sine theta. We repeated the previous steps to collect experimental acceleration. We then compared how changing the angle affected the acceleration and percent error.
Hello, my name is Jorge Valdez and we're doing the data analysis for our lab. So we started off by getting our sine of our incline. So for our height, it was our opposite. We had, it was 2 centimeters, and of course we had to convert it to meters, so it's 0.02 over 1. So sine theta is 0.02, and then to get our acceleration, we had to calculate that by gravity, so that came out to 0.1962, and then that's all that was on that's all the information on that I just said. And then for this is our theoretical, and then for this second table we had to calculate our experimental acceleration 1, which was low mass, meaning it had no mass on the slider, and high tilt, meaning it had a high height. And then our initial velocity from is this the first table? Yeah. Our initial velocity came out to, it was a negative 0.6, and then our final was 0.49. That we got our experimental acceleration, and our percent error came out to 32.5, which we got here by doing our theoretical minus our experimental over a theoretical. And then for our third table, we had to do high mass, high tilt, so that just means we added more weight to the slider, and our initial velocity came out to 0.08, our final was 0.16, our experimental was 0.2, and then our percent error for this one came out to 1.9%. So that one was a lot better than the first one.
Hello, my name is Santiago Arras. I'll be explaining the second half of the data analysis for Lab 5. So right here, we're right on step 3, and as you can see that we were directed to change the tilt of the track. So originally when we had about 2 centimeters of slabs on the tilt, we went ahead and just halved it, and we kept a centimeter of tilt within it. After different various experimental runs where we had a lot of weird sensor issues, we went ahead and after getting our opposite and our sine theta right here of the 1 centimeter, we got that was our new theoretical. We got precisely a 50% difference change because as I explained before, we swapped literally half the slab, so it makes sense there. Moving on to step 4, then we went ahead using our experimental from the graph right here. If you can look right over here, graph. We got a mean acceleration of 0.1 as we got right here using the graph, and we got a nice U-shaped slope right here to do it. And so using that, we got a percentage error of 1.9 using our old experimental for our lab report, and that'll be it.
Hi, this is Kason Kelly. In this experiment, we studied the motion of a car on an inclined plane to understand how acceleration behaves under the influence of gravity. Following Galileo's original setup, we observed that when a car moves upward, it slows down until it comes to a rest, and when it moves downward, its velocity continually increases. Our goal was to measure the car's experimental acceleration and compare it to the theoretical value calculated using the equation A equals gx sine theta, where g is the acceleration due to gravity. By adjusting the tilt of the air trap with slabs, we created different inclines and calculated the sine of each angle using the Pythagorean theorem. From our velocity versus time graphs, we found that the experimental accelerations were close to the theoretical ones, but not exact. Small percent errors appeared in our results, which can be explained by several factors. Air resistance and friction, although minimal on an air track, can still reduce the cart's motion and lower the measured acceleration. Additionally, slight misalignments in the angle measurement or sensor calibration could introduce error in our data collection. When we added extra weight to the cart, we noticed that the acceleration remained nearly the same. This confirmed that acceleration on an incline depends on the angle, not on mass, just as Galileo concluded centuries ago. However, the added mass could have affected the glide's balance, causing small variations in the sensor's readings or in how smoothly the cart moved. When we decreased the incline, the acceleration became smaller, which aligned perfectly with our theoretical prediction. Overall, our results verified the relationship between gravity, incline angle, and acceleration, with minor deviations explained by experimental limitations. This lab helped us better understand how gravity influences motion and why real-world conditions always create differences between theoretical and measured values. Thank you for watching.
Hi, my name is Gregorio Olivas and I will be going over the credits. So Steph did the introduction, Kason did the conclusion, Conrad did the materials and the procedure, Jorge and Santiago did the data analysis, and I did the procedure and all of the editing. Thank you.